Okay, so here we are. Here's kind of a summary slide. So to remind you what we did this week, everybody needs a good reminder every once in a while. We covered Dalton's atomic theory on Monday. There were 4 parts to the theory. Know those 4 parts. We talked about the structure of an atom and the subatomic particles and their charges and their mass. We talked about the unit of AMUs, okay? You need to know what that stands for. We talked about how they're arranged in an atom and why. We did some review questions on the poles, and then we talked about isotopes and their natural abundance and how we calculate an average atomic mass. So I'm going to actually, this right here is probably the most mathematical thing we did Tuesday. Remember, you actually have to calculate that. And depending on the number of isotopes, depends on how long that problem could be. So we worked a problem with copper, Cu. We did copper 63 and copper 65. And we calculated the average atomic mass. Remember, it's a weighted average. Now, with this problem, there was only 2 isotopes. Okay, but I encourage you, there's some from the back of the chapter in 2 that I'm going to post or recommend you work. There's times, I mean, there's elements with like 20 isotopes. Okay, now I would never do that to you on an exam. That would just take up too much time, and that's kind of pointless. I want you to know how to calculate this, though, for the exam. So if you struggled with that, we did it right here on this slide. All the work is gone because I downloaded a new set of the slides. But make sure you can do the problem on this slide right here, calculating an atomic weight, okay, from isotopes. Remember, we take the AMUs and we multiply it by the percent as a decimal. And we do that for every isotope and we add them all up, okay? So if you have questions on that, let me know, but make sure you're good with doing one of these problems. Hint, hint, cough, cough, okay? Periodic table. We're going to talk about that, how it's organized, what all information it conveys, which is actually a lot. And then we're going to talk about valence electrons today. So periodic table. Oh, I love this slide. I always have to tell a story when I love Tetris. Anybody play Tetris before? Please tell me that's not past your generation. So back in the day, my grandma, she's like 84 now, and she is feisty. I'm pretty sure anybody can be feisty when you're 84. You've lived long enough. You can say whatever you want to say, however you want to say it at that point. So she's 84 and we got her a Game Boy one year for Christmas. Anybody still play Game Boy? I will probably make fun of you if you do, but we got her a yellow Game Boy, and the one game we got her for her Game Boy was Tetris. And that woman played Tetris more than anybody that I have ever known. And it was always my goal when I went to their house to try to beat her scores. And guys, I never did it. So she still has the lead scores in our family. All right. Anybody play Candy Crush? You gamers, you? Okay. Periodic table. So this is not how they made the periodic table, right? It's actually very organized. There's 118 elements on the periodic table, and it's organized in a certain way. There's lots of information conveyed just from how it's organized. So let's start talking about how it's organized. So there's 2 dominant ways it's organized when you look at this. If you're into games, check out the chat. Somebody just talked about a gaming place in Fayetteville, okay? All right, purple section is called a row, okay? So the horizontal sections are called a row, or they are sometimes called a period, but I'm going to call them rows, all right? So row 1, row 2, but they're also known as periods. The red section over here, the vertical section, I call them groups. They are also known as families or columns. Okay. I call the horizontal section rows, and I call a vertical section a group. So if I say group 1 or group 2, you need to understand that kind of language moving forward. All right. So that's the simplest way it's organized. All right. However, if we scroll down, we see the same slide. So I've got these names up here. Remember, horizontal, periods or rows, families, groups or columns for the verticals. The ones that are highlighted on this slide, so group number 1, group number 2. And then over here, we'll actually talk about how we number these groups, but these groups that are highlighted, these have common family names. Okay, so you will need to know the names. Not for every group, but for these 4 that are highlighted, you'll need to know the common name because I'll use those and you need to know which group I'm talking about. So we'll get into that in just a minute, but you need to know these 4 groups are special and they're important, and you need to know the names of these. All right, let's keep going. Okay, let's look at these sections. Anything that's highlighted in red here, this is another way to kind of organize the table. These are called main groups. Okay, these are main groups. And again, it's four of those main groups. We'll learn the specific name for those. The blue, these are your transition metals. Okay. Green, these are called your lanthanides and actinides. I'm not going to write out the second word because I don't have enough space, but we're really actually not going to be spending any of our time studying the green section, the lanthanides and actinides. We're going to spend all our time on the main groups and the transition metals. All right, learning about those, learning characteristics of these, how they interact, so on and so forth. So main groups and transition metals are the most important to us, but that section down below, and if you'll notice this arrow right here, it means this whole section is actually supposed to be shoved up in between these elements that I've drawn a line between. And if you look at the numbering, so lanthanum and actinum, okay, that's the names of these elements that I just underlined. That denotes how we name this whole green section. That's why these are called, this top row is called the lanthanides, and this bottom row is called the actinides because they follow the element titled lanthanum and actinum. And if you look at the numbering, we have number 57 here. This element has 57 protons. And then you can see the next one over, hafnium, jumps to 72. Okay, so there's all these elements down in the green rows fit between those two elements. Okay, just so you know. They're not their own separate part. They're part of the table, but for space sake, that would be a really long periodic table if we actually printed it the way with all these elements up in the table. So for space and printing purposes, I guess, they pull those two rows down. All right, let's continue. Another way that the periodic table is organized is these sections here. In the yellow, all of these elements are metals. Okay, now at room temperature here on Earth, at normal life temperatures, metals exist as what? A solid, liquid, or a gas? They exist as a solid, right? So these elements at room temperature are solids. The exception, anybody know the exception? There's one exception. What metal exists naturally as a liquid?
Mercury.
Yes, mercury, Hg right here. So this is our one exception, but all these yellow elements exist naturally as solids. Okay, purple, so right over here, this kind of stair-stepped diagonal, these are called metalloids. All right, metalloids, why are they called metalloids? Because they have some characteristics of metals, some characteristics of non-metals. So some of these elements can conduct electricity like a metal, but some of them exist more naturally as a gas than a solid, okay? So they exhibit characteristics of non-metals. So everything in blue is what we just said, actually, it's a non-metal. And these exist naturally as gases. There's one exception though. Anybody know our one exception? Which one of these blues is a liquid? So over here, it's bromine, okay? So these are our two exceptions. These exist as liquids, and mercury and bromine. Otherwise, you've got solids and gases, okay? So that's important. If I tell you sodium, you know, if I give you that element, you need to know, okay, it's a solid at room temperature. If I tell you nitrogen, you need to know it's a gas at room temperature, okay? In fact, on the post-lab question for the wet lab, Group A people, the one you did last week, Group B people, there was a question about metals and gases, or certain reactions that we had on the data sheet, and did they produce the same gas? Well, if you understand that metals are solids and they don't make gases, that's going to help you answer that question. Okay, so that's another way the periodic table is organized. So now I told you certain groups, meaning a vertical portion, has a common family name, and this is highlighted. Now, one thing to point out here, we have not highlighted hydrogen. Okay, hydrogen is an exception in a lot of ways. And hydrogen is a non-metal, but it is put in group 1, okay, for reasons beyond this, okay, when it comes to how electrons are configured within an atom. That's why hydrogen is where it is, but we don't have to know that. So just know hydrogen is an exception. It's not a metal, but we call this group 1 the alkali, A-L-K-A-L-I, alkali earth metals. Okay. So wait, sorry, that's group 2. It's just alkali metals. Getting ahead of myself. Alkali metals here. All right. So group 2 is out. They're very similar, alkali and alkali earth metals. But group 1 are alkali metals. So if you look at these, you might even recognize some of these. Sodium, potassium, these are things we need in our diet, right? And then here's what you need to know about the alkali metals. I have some characteristics down here. They're highly reactive. So they tend to combine with other elements. They react very easily. And because of that, we don't really find them as a pure substance in nature, like out in our planet. They're usually in a compound, okay? So they're always found in compound form. They're very reactive. We don't find them as pure elements a lot. So that's the alkali metals. Now, I'm going to stop sharing my screen for just a second because I want to see, hopefully, if this will work. I have a video that I want us to watch. So I'm going to stop sharing with the iPad. I'm going to just share you with my desktop. Okay, hopefully y'all can see my screen. And I'm going to see, this is a reaction. Can y'all see? We're on YouTube now. Y'all can see YouTube. Hopefully you'll be able to hear it. I've never tried this. This is sodium metal, and this is a beaker of water. Now, sadly, the video I used to show for this, it wouldn't work. It's like canceled now. So this one's less cool in my opinion because it's a very small piece of metal. If I zoom back, I want to give you a good close-up. Okay, number 1, look what's happening here. He is literally cutting this piece of metal with a knife. Okay, so you can understand from that these metals are pretty soft and pretty malleable. All right, they're not really hard metals like a steel or an iron. So the group 1 metals are soft. You can cut through them with a knife, and in fact, when you do that, if you notice, once he's cut through it, you see that it's very shiny, very lustrous. Okay, it's another characteristic of these group 1 metals, very shiny. And then they're highly reactive with water. So let me find kind of where he gets going. So I'm going to play it.
Sodium metal and add it to water. We notice a much more rapid reaction.
I'm going to turn the sound of that off. So you can see it interacting. Now, because it's such a small piece of metal, you don't tell how violent of a reaction this normally is. You can tell it's kind of bubbling, kind of giving off some gas. But you can tell it's a reaction happening here. Now, usually if you take a big chunk of sodium metal and throw it in like a pond, you'll see some sparks, you'll see some fire. It's pretty explosive. He puts a bigger chunk in here. And so anyways, I just wanted you to see that. It's very reactive. Stuff starts happening immediately. Now I want you to see, so that's sodium, and sodium is right above potassium. So now we're going to watch this video. I'm actually going to turn the sound on for this because I want you to hear it.
Yeah. Ready? Yeah.
Okay, so let's watch this one more time. He takes a little chunk of potassium.
Yeah.
It's right beneath sodium. Throws it in with the water. Okay, now, so let's talk about this. What was the difference in the 2 reactions with sodium and potassium? What did you notice? Anybody?
Potassium was more like violent, or like, you know what I mean? Like it reacted real quick.
Yeah, I think violent is an okay word. Anybody else had any other thoughts on how those were different? Okay, well, I think Elias summed it up pretty good, that potassium reacted a lot quicker, a lot more violent. So as you go down, so let me pull up a periodic table again. Let's look at this really quick. I'm going to share my screen again. So here is, let's zoom in. Here's sodium right here. Oh, my pencil, right here. And then potassium is K right underneath it. Now, what if we took RB right here is rubidium? Oh, goodness, what happened? RB is rubidium. What do you think would happen if we threw a chunk of rubidium in with water? What do you think would happen if we threw a chunk of, this is cesium, in with water? Do you think the reaction would become more violent or less violent?
More violent.
Yes, you are correct, okay? So there's a trend here. As you go down this group, they become more and more reactive, all right? So I just wanted to give you all a visual of that. If we were really cool, we would actually go do these experiments in person, but we can't. Okay, so that's group 1. Let's talk about group 2. There's those links. This one didn't work, so I had to find a new video, but this is the one we just watched. All right, common group 2 is the alkali. Okay. These are the alkali earth metals. All right. Now, these are similar to group 1 in several ways. They're very reactive. You don't find them as pure substances very much. But I will say they're less reactive than group 1. Okay, so these are less reactive than group 1. And remember, we're excluding hydrogen when we say group 1. Okay, so magnesium, beryllium, calcium's in group 2 here, alkali earth metals. They're similar. They are reactive, but less so than group 1. All right. So that's the common name for group 2. We're actually going to move on now. Group 7. So this was the other group I said had a common family name. You need to know this one. These are called the halogens. So we've been over talking about metals. Now we're talking about nonmetals. Okay, so if you notice, all of these halogens exist as gases except for bromine. Bromine is a liquid at room temperature. Okay, so fluorine, chlorine, iodine, these are our halogens. And then these are corrosive. Okay, they're colorful. Chlorine gas is a very toxic, corrosive gas. Again, they're nonmetals. Here's what you need to know about group 7, the halogens. They commonly react with group 1 metals, and we call the product of their reaction a salt. Can anybody name a very common one that we should know, like chemically, between a group 1 element and a group 7? You see one? NaCl, sodium chloride. Okay, there we go. Somebody typed it. I put another link down here at the bottom if you want to watch the reaction between sodium and chloride or chlorine. Chlorine is a gas. Sodium is a metal. So we have a gas reacting with a metal. It's a very violent, fiery thing. And then you get this very docile, edible salt afterwards. Isn't chemistry weird? How we can take a corrosive thing and then a metal, which we would never eat, and we can put them together and make something that we eat every day. So anyways, group 7, that's the halogens. And then group 8 is the last group with a common family name. These are the noble gases. Noble gases, okay? All right, so the noble gases, these are not reactive at all right? So they are not reactive. You don't find them in a compound form. You often find them as pure substances. They don't like to react with anybody. They're good just by themselves. And there's a reason for that we'll find out later today and kind of into next week. Now, one thing that you need to know, and I don't know if some of you have spotted it, if you look at these numbers up here, you see how it says 1A, 2A, and then look, we have a numbering continued, but the letter changes, 3B, 4B, 5B, and then when we get back over here, we see another numbering, 3A, 4A, 5A. What's that about? So I want to explain this really quick. Remember, I'm going to scroll back up to a different picture of the periodic table. Right here. Everything in red, we call the main group. We have a specific way for numbering those. And that's what you were seeing down below. Everything that has a number and the letter A that is denoting a main group. So that's why you saw 1A, 2A, and then it skipped over here and we called this 3A because we're just continuing to number only the main groups, 4A, okay? The B portion, the reason we called this B down here, or sorry, B, 3C, or yeah. So, whoa, I labeled this should have been B. No, sorry, I'm getting confused. This was A. And then this is all B down here, 3B, 4, sorry guys, letters and numbers are hard today. 3B, 4B, 5B. Okay, so we continue numerically, but we keep the letter as B. That's because the A is denoting a main group. That's important. I want you guys to know how to count main groups. And when you count main groups, you skip the transition metals. And you go straight over here to main group 3. And then you continue counting 3. This would be main group 4. This would be main group 5, main group 6, main group halogens are main group 7, and the noble gases are main group 8. Okay? So if you're wondering about the A and B stuff like you see down here, that is why. These are the main groups. These are main groups. And then the B denotes a transition metal group. Okay? So technically there are 18 groups across the periodic table, but we number a portion of them differently if it's a main group, okay? All right, we talked about halogens, we talked about noble gases. Okay, I want to mention this for just a second, periodicity. This is a very unique property of the periodic table. There are trends on the periodic table. We're gonna talk about 3 of them between this week and next week. But I want you to look at this first graph. Okay, I'm gonna zoom in on it, try to make it as big as possible. In fact, I'm gonna turn my screen sideways. Okay, let's look at this graph. So on the y-axis, we have the atomic radius. Now, everybody remembers from geometry what a radius is. If we have a circle, and atoms are a circle, they have the nucleus, and then here's the electron cloud. The radius is just the measurement from the edge to the middle. This would be the radius. I'm going to label it R. And this is how we measure the size of atoms, okay? We just measure the radius. We don't have to measure the full diameter. We could. We just measure the radius. If the radius is getting bigger, the atom is getting bigger. So that is what the atomic radius, that's the unit here, or that's the label. Now, what do y'all think PM stands for? I mentioned this on Tuesday, I think. It's a picometer. It's way, way, way smaller than a nanometer. And y'all don't have to know pico, but I want you to understand that's what that unit is right there. Okay, and then on the x-axis, we have atomic number. So this is just listing all the elements in order from 1 to, 100 or so. Now, if we look at this, what do you notice? Here's what I notice, a periodic spike in the graph. Okay, now let's look at what elements are at the peak of each spike. We have lithium, we have sodium, we have potassium, rubidium, cesium, and francium. What is the similarity in all of these elements? These are all our group 1 elements, main group 1. So what does that mean? That means these elements tend to be the largest element in their row, or tend to be larger elements, yeah. And if you look at the bottom of each spike, what do we have? We have hydrogen, then we have fluorine, chlorine, bromine, and iodine. All right, and what are fluorine, chlorine, bromine, and iodine? These are all our halogens right here. Group 7, main group 7. So the small, and in fact, let's look at this a little closer. If we go from, for example, potassium down to bromine, notice the size of the element is getting smaller and smaller and smaller. The atomic radius is going down, 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 down. All of these elements, potassium over to bromine. Let's go look at this. I'm going to increase the thickness here. That's this row right here. So I just box that in. So all of those elements are in the same row. Which element was the biggest? Which element was the smallest? Well, potassium was the biggest and bromine was the smallest. Notice we're kind of skipping over the noble gases. They can be exceptions sometimes. So what does that mean? As you go from left to right across the periodic table, as you go from left to right, what happens to the atomic radius? It shrinks, it goes down. So elements in main group 1 tend to be the largest element in their row, and the halogens tend to be the smallest element in their row, size-wise. Okay? Now, if we're looking at just group 1 here, lithium, sodium, potassium, rubidium, what do you notice? The size of these group 1s tend to get bigger. The atomic radius increases as you go down, okay? So we're gonna draw a picture. I'm about to draw a picture. I want you to draw this in your notes with me. I put a blank slide in here just for this. We're gonna draw out the trends in atomic radius. Here is my periodic table. I gotta make it perfect. I don't have to make it perfect. Okay, there's a periodic table. So as you go across from left to right, I want you to know the trend. Atomic radius decreases. Okay. As you go down vertically, what happens? I'm gonna try to write sideways. Atomic radius increases. As you go across from left to right, atomic radius decreases. We saw that the halogens, which are group 7, are smaller than the alkali metals and alkali earth metals. And then we noticed that like cesium and francium and rubidium, which are down at the bottom of main group 1, they were bigger than, say, a lithium and a sodium, which are up towards the top of main group 1. I want you to know these trends. How could I ask you a question on this? If I picked 4 elements, if I said, you know, sodium, carbon, chlorine, and I picked a noble gas, neon, and I said order them, put them in order of increasing or decreasing atomic radius. You should be able to do that by looking at a periodic table and knowing these trends. Okay? So know this trend for sure. So that is one type of periodicity on the periodic table, atomic radius. I'm not going to talk about this one as much, but melting point versus atomic number. So as you increase in atomic number, what happens to the melting point where periodically, again, you get a spike, okay? I'm noticing a couple of things. Carbon, silicon is at the top of a spike, Ge, germanium. So let's go look at where these elements are. They tend to have higher melting points. That is group 4. Carbon, silicon, germanium. I don't know, something special about group 4. They tend to have the highest melting point. So again, you don't have to memorize this. There's no trend we're going to draw. But I just want to make the point that there are specific systematic trends based on how this is all organized. Okay, so there's a lot of thought that went into the periodic table.
So with the sodium, carbon, and chlorine, what would be the correct order for those? Because I'm not understanding it. That's kind of confusing me.
Okay, well let's roughly see where are these elements on the periodic table. Sodium, let's go see where's sodium. Sodium is in what group?
1.
Okay, sodium's in group 1. So I'm going to write that down here. It's in group 1. Where's carbon? It's in main group 4. So I'm going to put a little star. Sodium's roughly over here. Carbon was like right here. What about chlorine?
7.
7. And neon?
8.
8. So with this trend, as you go from left to right this way, we said atomic radius decreases, right? Okay, so that would be how you would order them. In fact, I didn't ask a question increasing or decreasing, but I said put them in order of decreasing size. This is how you would order them from left to right. Does that make sense? Now, if I gave you elements that were mostly in the same group, up and down, then you would look at this trend and you would see that as atomic radius, as you go down the periodic table, we said atomic radius increases. You would keep that in mind for ordering them vertically. If their placement was like, you know, right here, here, and then I had another one here and another one here. Okay. Does that help, Aaliyah?
Yes, ma'am.
All right, so that is the periodic table. What do I want you to know? I want you to know the names of main groups. I want you to know how to count main groups. I want you to know, if I ask you, what's the state of element, blah, blah, blah. Is it a solid, a liquid, or a gas? I would want you to know that. Know our two exceptions, mercury and bromine are liquids. Everything else is either a solid if it's a metal or a gas if it's a non-metal. And then I want you to know this trend in atomic radii, okay? All right, now we're going to talk about valence electrons. Okay, so when scientists realized that there were trends in the periodic table, they had a question. They were like, why? Why are we seeing these trends? Why is this happening? And it all has to do with how the electrons are arranged, okay? I used to make people learn what we call electron configurations, which are basically, it's like a shorthand notation for how electrons are arranged, but it's really not pertinent to your future careers. So we don't memorize those anymore. But I still want you to understand that the arrangement of an atom's electrons has everything to do, it determines its chemical properties. And we said that with that table that we filled in on Tuesday when we talked about the different roles of protons, neutrons, and electrons. We said the electrons are responsible for the chemistry. Now, if you look at these pictures on this slide, you really don't have to pay attention to this one over here, but I want you to see we're most familiar with this picture from Tuesday. We said here is the electron cloud, and we said here is the nucleus. All right, so we learned that. Now today, we're going to become more familiar with the picture of an atom like this. Kind of looks like layers of an onion, all right? Electrons, we said, are always moving about the electron cloud. Okay, we drew arrows and we said they're zooming about, they're flying about. But here's what you have to know. Electrons cannot just be anywhere in that cloud. They can only be at certain distances from the nucleus. And that's what this picture over here on the left indicates. An electron could be, it could be here, it could be here, or here, but it cannot be here. It cannot be in between these layers, okay? Now, electrons have different amounts of energy based on how close or how far they are to the nucleus, all right? What's really, really funny is when I had a baby shower for our first kiddo, so our daughter, Finn, when one person got me a gift, they got me a book that said Quantum Physics for Babies, right? So it's funny. I seriously would almost bring it and read it to you guys in lecture because it literally walks you through this in such simple language. But this is the reality, is that electrons can only be certain distances from the nucleus, and based on their location, they have a different amount of energy, all right? So the arrangement is determined by location within the atom of an electron and an electron and energy. All right, that arrangement is determined by location of an electron and the energy of an electron. All right, now what we call this picture is, we say the amount of energy that an electron can have is, we use this fancy word. I'm going to write it out and I'm going to explain a little bit, but then we're going to move on. We say that electrons, trying to figure out where to write this. So electrons have okay, here's the word, quantized. Quantized energy, meaning it has a certain quantity. It's not like a continuous slope. The best way I like to explain this, they have quantized energy. The best way I like to explain this is a set of stairs versus a ramp. Okay. If you are handicapped and you're in a wheelchair, you have to have ramp access for any building that you go into, right? And we know a ramp looks like this. All right, so maybe here's a ramp. Well, if you're not in a wheelchair, you can walk up a set of stairs to get into that building. On a ramp, I could be anywhere along the ramp. I could be here. I could be here. I could be anywhere in between on the ramp, right? But not so with stairs. With the stairs, I can be here, okay? Or I can be up here. But right here, I cannot be there. I can't be on that spot, all right? So there's certain places you can't be on a set of stairs. Unlike a ramp, you could be at any spot. And that's exactly the way it is with electrons. I drew electrons on the places they could be, these layers of an onion, but they can't be in between. Okay, we call that quantized energy. Now, that's as far as we're getting with the quantum physics of electrons. You don't have to know all of that, but what I do want you to know is what the word valence means. What is a valence shell electrons? Or electron? That is an electron in the outermost shell. So these layers of an onion that I keep talking about right here or right here, these circles that continuously get bigger around the nucleus, these are called shells. All right, so if I draw a picture of an atom, I'm going to zoom in. This would be called shell number 1, the circle that's closest to the nucleus. If I draw another one, this would be called shell number 2. This would be called shell number 3, and so on and so forth. And I'm going to point out one more thing. Let me go back to a picture of a periodic table. Right here. Let me find one. I don't really have a lot of space on the edge here. Sorry that I keep scrolling. Actually, I'm going to just draw it right here. If I'm drawing a periodic table, okay, it looks like this. And we know that it's divided into rows. As you go down, so if you're in row 1, we would say that electrons on the outermost shell there would be on shell number 1. So as you go down in rows, you increase the amount of shells that an atom can have. So for an element down here, it could have 4 shells around it, meaning it could have 4 circles around it. 4 layers to the onion. 1, 2, 3, 4. Now do you understand why atoms get bigger as you go down? Atomic radius increases because there's more shells, there's more layers to the onion as you go down, okay? So if we have an atom or an atom of an element on row 4 of the periodic table, it's got 4 energy shells around it, okay? Just wanted to make that connection for you. All right, but what is a valence? So because we have different shells, a valence electron is an electron that's found on the outermost shell. It is not on the inner shells. This one is a valence. Okay, you may have electrons on those inner shells, but they're not valence. Valence are the ones on the outermost shell, all right? Now, scientists noticed something interesting about elements who had similar numbers of valence electrons. So down here at the bottom, elements that have the same number of valence electrons tend to have similar group properties and chemical reactivity. Okay? Elements that have the same number of valence electrons tend to have similar group properties and chemical reactivity. So which elements have the same number of valence electrons? And the answer to this question is actually very easy. Elements that are in the same main group have the same number of valence electrons. I'm gonna write that statement right here. Elements in the same main group have the same number of valence electrons. And I'm just abbreviating with our symbol for electrons here. This is maybe the most important thing I say today. Elements in the same main group have the same number of valence electrons. So that's why I put these elements right here. Fluorine, chlorine, bromine. What do you know about these? They're all in main group 7. So they all have the same number of valence electrons. Any element that's in the same vertical column, remember that's what we call a group. They have the same number of valence electrons, and they're going to behave similarly. So why did all the alkali metals react violently with water? Why do they all react violently with water? Because they have the same number of valence electrons. Why are all the noble gases inert? Because they have the same number of valence electrons, and therefore they have the same kind of chemical reactivity. Okay, Tio, take care. I hope your family's okay.
Question about that.
Yes.
So how many valence electrons do the transition metals have? Because they're not like in the same group thing.
You're correct in asking this. It's a great question. They all have 2. Okay.
Oh, okay.
Transition metals all have 2 valence, so you can write that down. We'll actually get to that more in chapter 3. So you don't have to worry about that right now. Right now we're focusing on the main groups, but all the valence. Notice that all the transition metals. Let me look at a periodic table. All the transition metals, these are not in the same group. I've got, let's see, I've got chromium right here, and I've got silver, Ag, over here. They're in different groups, but they all have 2 valence. Okay, so transition metals are an exception here. Everything in that block, that's the transition block, and you could go up and look at how we organize the, there's a color coding of the periodic table that blocks off all the transitions in blue, I think. They all have 2 valence. So great question there, Abby. Any other questions so far on what a valence electron is and understanding that elements in the same group have the same number of valence? Okay, so I want you to know how to count valence electrons as you go across a periodic table, and it's real simple. If you know how to count main groups, then you know how to count valence electrons. So we said this is main group number 1, all right? So main group number 1 has 1, I'm going to abbreviate, valence electron. So hydrogen, lithium, sodium, potassium, and down, 1 valence electron. What does that mean? That means in their outermost shell, however many they have, remember the number of circles around the nucleus, the number of layers of the onion, it increases as you go down. But wherever their outermost layer is, they just have 1 electron on that outermost layer. So I just drew a picture of lithium right here. Why? Lithium is on row 2. So it's got 2 circles around the nucleus, and it has 1 valence electron. I'm going to draw a picture of hydrogen. How would you draw a picture of hydrogen? Draw the correct number of circles around the nucleus and draw the correct number of valence electrons. Hydrogen is on row 1. So we draw 1 circle around the nucleus, 1 shell, and we draw 1 electron on that shell. That's hydrogen. Okay, let's draw a picture of cesium. Well, what row is it on?
6.
Okay, 1, 2, 3, 4, 5, 6. Okay, this one's going to be big. I'm going to start small. There's 1, 2, 3, 4, 5, 6. Okay, and then we have 1 valence. So there's cesium. All right. So that's main group 1. Main group 2, they have 2 valence electrons. Okay. So if I wanted to draw a picture of barium right next door to cesium, all I got to do is put another electron here. Now we're talking about barium, not cesium. Okay. Let's skip over here to main group 3. These have 3 valence electrons. What are you noticing? The number of valence electrons matches the main group numbering. I'm gonna make a statement of that. The number of valence electrons matches the main group number. Okay, so how many valence electrons does main group 4 have? They have 4 valence electrons. Main group 5 has 5 valence electrons. Main group 6 has 6 valence electrons. Main group 7 has 7, and main group 8 has 8 valence electrons. That is how you count valence electrons.
Okay, I don't know if this question is overstepping like what you're talking about, but so let's say you have 6 valence electrons in group 6 of the main groups, and you have the element S. I don't know what it's actually called, but
Sulfur, right here.
yeah, and you only have 2, or is it 3? 3 shells.
Yeah.
So
you
how would you know where the electrons would go?
Okay, well, if we wanted to draw a picture of sulfur and we're just drawing the valence electrons, you would draw 3 shells, right? And then you would put 6 electrons on that outer shell. Does that make sense?
Okay, yeah, that makes sense.
Yeah.
I kind of had a brain fart.
Have that
Thanks.
6 valence electrons, yep. So that would be sulfur. We said this was barium. We said this was hydrogen. We said this was lithium. Okay. All right. Now, why? Why do valence electrons work this way? Why are they numbered this way? Well, we said valence electrons are the outermost. So a little bit more to know about valence electrons. Outermost electrons in an atom, and therefore they are the most loosely held electrons. Remember that electrons are pulled by the nucleus. They're being pulled in. Why? The nucleus is where the protons are. Okay, so if we have a positive charge in the middle, there's our nucleus, and we have some electron floating around it. We said there was an attraction, all right? There's an attraction here. That electron is being pulled towards the nucleus. But when you have an electron on shell number 1 versus an electron on shell number 3, this valence electron, it doesn't feel the pull of that nucleus as strongly as the electron that's closer. Okay? So that's why we say valence electrons, they're the outermost, they're on the outermost shell, therefore they're the most loosely held by the atom. Electrons on inner shells, they're more tightly held to the nucleus, or pulled by the nucleus, attracted to the nucleus, because that's where the positive charge is, because that's where the protons are. Here's another thing to know about valence electrons. All atoms, they want to have a full outer shell of 8 valence electrons. A full outer shell. So the most valence electrons we saw when we numbered valence electrons, let's go look at our table up here. The most we got to was with the noble gases. This is 8. And this is what we call, I'm actually going to erase that. This is what we call a full outer shell. When you have 8 valence electrons, you have a full outer shell. Now, does anybody remember we said that the We said the noble gases were special. They aren't like other elements. In what way were they different?
They're not reactive, right?
They're not very reactive. They're inert, okay? They don't have a lot of friends, all right? They're your introverts. So the thing is, there's something very stable. We use that word stable when you have a full outer shell. And because they're stable, they don't need to react with anybody else. You figure out in chemistry, all the elements, they want to be stable, all right? We just have some elements that are less stable than others, okay? It's the same with people, right? We all want stable families, stable jobs, stable routines. Some people have a harder time. Some people, due to life circumstances, you know, and rightly so, like some people have a harder time. Some people are a little less stable than others, and that's okay. We're all trying to make our own way. But sometimes I like to give analogies, okay? But there's something very stable and very satisfying to an atom when you have a full outer shell of 8 valence electrons, all right? Now, what we're going to get into with chapter 3 is this statement right here. Atoms will give away or receive valence electrons so that they have 8. They'll do anything to get 8. They'll give away electrons. They'll gain electrons so that they try to get 8. That's why I put this little picture here. They'll trade their valence. They won't trade other electrons. They only trade the valence. So, for example, let's read this example. An atom with 5 valence electrons. So that's in main group 5. So we could be talking about nitrogen. He's in main group 5. He's got 5 valence. He will receive 3 more to achieve an outer shell of 8 valence electrons. Okay. On the other hand, an atom with 2 valence electrons will give those 2 away because underneath they have a full shell of 8. All right. Now, what you're going to learn, I don't have space. I'm going to erase a little bit. Hopefully you've gotten these pictures of all of our atoms down. Based on what we just said, here's what you can learn. Elements on the, let's see, this is the right side. Okay, elements on the right side, they tend to gain electrons. Elements on the right side. Now the exception here is group 3. You'll find out that you can give away 3 quicker than you can gain 5. So right side meaning kind of on the right of main group 4. So that would be your main group 5, 6, and 7. These tend to gain electrons. The elements on the left side, so your transition metals, anything with less than 4 valence electrons, so anything with 3 valence electrons, 2 valence electrons, 1 valence electron, these tend to give away valence electrons. So the right side, main groups 4, 5, 6, and 7, they tend to gain electrons so that they get a full set of 8. Left side tends to give away valence electrons to get a full set of 8. All right, last statement, and then we're going to move on to electron dot structures, and then that's it for today. It happens that elements within the same group, we mentioned this, they have the same number of valence electrons, and therefore they trade electrons in a similar fashion. I hope you understand what that statement means. Because elements in the same group have the same number of valence, they will trade electrons in a similar fashion. So if we're looking at main group 1 here, lithium is going to trade electrons the same way cesium would. They're both going to try to give away 1, all right? Magnesium would trade electrons the same way calcium would because they have the same number of valence. All right. So that's a little bit about valence electrons. Don't y'all love how I have like this whole slide underlined by the time we're done? On like every slide. Do I do that? All right, electron dot structures. This is pretty much the last thing I want to communicate to you today. Electron dot symbols for some main, notice we're just talking about the main groups here. We will not draw electron dot structures for any element that's not in a main group. I basically want you to be able to quickly represent and draw out how many valence an electron has. That's what an electron dot symbol does. Symbol, structure, same thing. So all you do is you write the symbol for the element, which is the letter or letters for that element, and then you put a dot, one for each valence. So if you are in main group 1, these have 1 valence electron. So you're just going to put 1 dot. And then as you go across left to right on the periodic table, as you increase in the number of main groups, you add a dot. Now notice you need to add 1 dot to each side before you ever double up and put a second dot on the same side. So that's why group 4, we don't draw a carbon like this. Okay, we spread out, we put 1 dot on each side. And then once we hit group 5, we only have 4 sides. So then we start to double up, and you can put 2 on one side, okay? And then group 8, they have 8 valence. So you're going to put 2 dots on each side. The only exception here is helium. Helium has 2 valence, all right? Helium is an exception. Even though helium is in main group 8 and it is a noble gas, there's something special. I'm going to draw a picture of helium. Here's the nucleus. It's on row 1, right? It's on, if we look at a periodic table. Here's helium. Helium is on row 1. With hydrogen. Helium and hydrogen are the only 2 elements on row 1. So we just draw 1 shell around the nucleus. There's something special in chemistry about that first shell. That first shell can only hold 2 electrons, and once it hits 2, it's full. It can't hold 8. So that's why helium's an exception here. The first shell can only hold 2. Subsequent shells, so if we drew a second shell, that shell could hold 8. A third shell, that shell could hold 8, but the first shell can only hold 2 valence electrons. 2 electrons, period. All right. So just know helium's an exception. If I have you draw the electron dot structure for helium, don't put 8 dots around it. All right, so let's look at this. Give the number of valence electrons and draw the electron dot symbol for these following atoms. We're going to do this, and that's all I have for today. Kr. Where is Kr? Kr is right here. It's a noble gas. It's in main group 8. So how many valence does it have, and how would you draw its dot structure? So we say it has 8 valence electrons, and you draw the symbol, and then it's actually right here. You put 2 on each side to show all 8. Okay, carbon. I'll tell you, carbon is in main group 4. So write out how many valence does it have, and how would you draw its dot structure? So if it's in main group 4, remember the way you number valence, it matches the main group number. So 4 valence electrons, and you're going to draw the symbol and put 1 dot on each side. Okay, what about, let's do calcium, Ca. Calcium is in what main group? Anybody know?
Two.
Main group 2. So therefore it has 2 valence. So if we draw the picture over here, calcium, I don't care if you do it top and bottom, left and right, but just 2 dots. Okay. All right, what about, let's skip potassium, let's do boron. Boron, anybody know what main group boron is in? It's in main group 3, so it has 3 valence. And you draw the symbol, and you can put 1 dot on each side. So I think that last one, chlorine, main group 7, so 7 valence. And so you're going to put 1 on each side. That's 4. Now we need 3 more. It does not matter which 3 sides, but 3 of those sides, you'll double up the electrons. Okay. So you should be able to look at an electron dot structure or symbol and tell me how many valence are in that for in that atom or that kind of element. Okay. All right. Well, that concludes. We're wrapping up a little bit early today, but if there's any questions, I will stick around. Make sure you get the quiz done today. Make sure you get all your lab work done today or by tomorrow. And enjoy Monday off, and we'll see you again on Tuesday.
Can I ask a question about the homework, the dry lab?
Yes, and remind me, it's Maria?
Yes.
Okay.
Okay, so for the specific heat questions,
Yes.
I could not find the formula. Like I looked online and they just kept giving me different ones and I don't know what the formula is.
Do you have the lecture, the measurements lecture?
Yes.
Those slides? Yeah, the formula is on there.
Okay.
If you go down, so we started talking about temperature, and then right after temperature, we talked about, I can't remember if we talked about density or specific heat next, but where we're talking about energy, there's a big heading, it says energy. In fact, I'll pull it up right here. So we talked about specific heat and then density. So let me share my screen really quick. Okay, right here. Here's your pencil. Here's your equation. Now notice this top part, it's either calories or joules. So the problem will always give you the energy term in either joules or calories.
Okay, that's what I didn't know if you had to change them to calories or joules. So it could be either one.
Well, yeah, and sometimes the question will want you to solve for that term. Okay, so for example, this question here said, how many joules? So if you remember, we actually worked this out in lecture. We were solving, we just wrote the equation like this. We said specific heat equals, I'm going to pick joules because that's what the question wants the energy in. So I'm going to ignore calories. And that's over grams times degrees Celsius.
Uh-huh.
And remember, this is we said delta T. This is your change in temperature. It's not a static temperature. So if you're given 2 temperatures, you need to find the difference and plug it in as a positive number. It should always be positive.
Okay.
And then not only that, but based on what the question's asking for, if it's asking for joules or calories, you need to pay attention to which specific heat you plug in. Because often specific heat can be given to you in calories per gram degree Celsius or joules per gram degree Celsius. So here, because we were wanting to solve for joules, I'm going to pick a specific heat from this column based on what my substance is.
Oh, okay.
It's talking about ethanol. It was asking us about ethanol.
Mhm.
So if we look at this, ethanol is that very first one listed right here. Which specific heat do I use?
The 2.5.
Yes, because we want it in terms of joules. You need the energy unit and specific heat to match the other energy unit given. Okay. Now a lot of those questions on the dry lab, you're solving for different terms. You're solving for the grams or the change in temperature, and energy will be given to you. It'll say this many calories or this many joules was invested, or however it says it. But if it gives you joules, you need to use a specific heat that has matching units, joules. If it gives you calories, you need to use a specific heat term that has calories.
Okay,
Makes sense?
Thank you so much.
Yeah, is that it?
Yes. Have a good weekend.
Okay, you too. All right, I'm gonna hop off. Jalen, do you have any questions?